Okay, we are here today at day 14. The task today is to look at some limit laws, kind of things that we would probably do with limits if we didn't have them, but thankfully they give us some rules or laws to go by with regard to evaluating limits. So this is chapter 2, section 3 of your book. Keeping in mind that a derivative, which is right around the corner, is a limit, and we want to know all the different things we can do with limits and look at a lot of different examples today of limits so that we can handle these things called derivatives when we encounter them. So these are their limit laws that I've got up here on the screen in that not so pretty blue color. Unfortunately, that not so pretty blue color happens to project well. So we're kind of stuck with that, but if you're wondering why we use that, that's why. First of all, if we start with some functions that in fact their limits do exist, some f of x as x approaches a, and some g of x as x approaches a, so we know that they have limits. Then if we have the limit of the sum of these two functions, it is the sum of the limits. Does that make sense? That we've kind of already used that already, right? Yeah. When we had some pieces and we took the limit of each individual piece and just added our answers together. The second one, the limit of a difference, is the difference of the limits. So the limits have to exist or we couldn't use these. They wouldn't make sense. The limit of a constant times a function is a constant times the limit of the function. Kind of just bring that coefficient, that constant along for the ride, and then just evaluate the limit of the function itself. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, as long as we don't introduce some zero in the denominator by throwing the g of x into the denominator. So those are things that we would probably do if we didn't have the limit laws. All of these can be proved. It's a pretty formal, kind of rigorous proof. You can see these formal proofs in appendix, I believe it's appendix D in the back of the book. We're not going to go into quite that rigor right now. Not that we shouldn't think of calculus, at least Math 141 in an engineering sequence, which this is. We should think of it as a fairly rigorous course, but that doesn't mean we have to go into the background of everything we develop. Another thing that we're allowed to do with limits, we have a function to the nth power. We can take the limit of that function and then take that result and raise it to the nth power. The limit of a constant is in fact that constant. It doesn't matter what x does. X could go to a or b or c or q or r. C is never going to change from c regardless of what x approaches. The limit of x as x itself approaches a, well, that pretty reasonably ought to be a. So that's kind of a linear model there. The first one is linear, 7 is linear also, but it's a constant function. The next one is linear, but the y value is the x value, so as x goes to a, we would expect the y value, if it's x, to also go to a. If n is a positive integer, the limit of x to the n as x goes to a ought to be a to the n, so you can kind of get a feel for the shortcuts that are going to result from this set of limit laws. We have the nth root of x, so this same property if the exponents are integers, same property when we have nth roots. We're assuming a natural domain. If we have an even root, we've got to have a number greater than 0. And the nth root of some function, we can then evaluate the limit of the function and take the nth root of that result. These are things that you'd probably do if we didn't have laws to allow us to do that. So we'd kind of have a different, very different approach to limits and derivatives if we did not have these. Now what I'd like to spend some time on are some examples. This is probably, you would consider this to be a little bit over the top, and we're certainly not going to do this on every problem, but let's at least look at an example or two where we actually impose the limit laws and then we'll just kind of use them. They'll move into the background. So let's suppose that we have this problem, the limit of just a simple polynomial and we want x to approach, it doesn't really matter here. Polynomials are continuous everywhere, so it's not like there's a bad value. So as x approaches 3, according to the limit laws, this ought to be the limit of x squared minus the limit of 7x, x going to 3, and we could, I guess, continue to use these limit laws. And in fact, we have some choices with regard to some of these as we simplify them. The limit of x squared, we could think of that as x times x. This could be 7 times the limit of x. That's legal, right? According to one of the limit laws, we can take that coefficient and bring it out in front. Limit of 5, well, that's the limit of a constant, so I'm just going to leave that alone. Doesn't matter what x approaches there, that last piece is 5. Do you agree with me that we've got a little kind of overkill going here? That why not just, you know, it's a polynomial, it's continuous everywhere. What's the problem with just plugging in 3? Because we know we're going to approach that value, and in fact, at 3, we attain that value. Umair?
Aren't we supposed to like square the whole limit?
You could.
Limit x squared?
You could. We could take the limit of, I'm using, there's a couple of things we could use. I'm using the limit of a product as the product of the limits. But you're taking another one of the limit laws, which is fine. That's the one, that's the direction I was going, but you could go that direction as well. So we're not really ever going to do that, but that's how we could break it down into pieces. The limit of x as x approaches 3. Limit of x as x approaches 3. We take their product. 7 times the limit of x as x approaches 3. And the limit of a constant as x approaches whatever you so choose is that constant. So what's wrong with, if you look at what we have here, that's just 3 squared, right? Minus 7 times 3, well, that's minus 7 times what x is approaching anyway. And we've got a 5, which is unaffected by whatever x is doing. So is there a problem with, in a polynomial or some function that's not suspect at all, just putting the value in and running it through the function? Not a problem. Okay? And in fact, you will see that particular notion in your text. This direct substitution property. If f is a polynomial, which we just had, or a rational function, and a is in the domain, so a is not a bad value, it's not a vertical asymptote, it's not a point that creates a hole in the graph, so it's a simple, benign, kind, nice value, there's nothing wrong with direct substitution. But in the background of that direct substitution is this series of limit laws. Is that okay? That's there, we're allowed to do that, and if a is itself a pretty decent value, not a bad value, then we're okay just to substitute. Now some problems can take on a little, polynomials, this is a polynomial, are really never an issue because they're continuous everywhere. You could have another problem that is not quite as nice, but the procedure is in effect the same procedure. So you ought to be a little leery when you see a problem like this that we've got a bad value going on here, right? The bad value is 3. We should be a little suspect, certainly at 3 and clearly near 3. But if x is approaching 4, that's not an issue, is it? Can we just substitute in directly and evaluate the limit? Yes, we can. So we should expect to get 2 4s plus 5, 4 minus 3. What do we get there? 13. So it actually takes on that value. When x is 4, the y value from that function is 13. So as x is approaching 4 from either side, we would expect the y value to be approaching 13. So direct substitution is a nice little property if it's not a bad value. Now, when would direct substitution be a problem, be an issue? Question? Does somebody have a question? Sorry, maybe I'm hearing things. Is direct substitution a problem there?
Yes.
Yeah.
If you did substitute in directly, what would you get? Which is a good indicator that we've got to do some other method.
0 divided by 0.
0 divided by 0, which is what? How many people in here? 24 people? Could we have 24 different answers for 0 divided by 0? We could have a lot more than that. 0 divided by 0 is whatever you want it to be. So when you get an answer of 0 divided by 0, it's as if you haven't even started the problem yet. So we've got to do something else. Something is causing division by 0. In fact, even worse than that, something is causing 0 over 0. What is that something in this problem?
3.
The factor x minus 3, right, is in the top and also in the bottom. So when direct substitution fails, let's try some algebraic manipulation. We've done a little bit of this already in this course. Can I reduce, or can you reduce, x minus 3 over x minus 3? Does it always reduce to 1? Doesn't always. In fact, we just talked about when it does not reduce to 1, and that's when x is 3. So if x is approaching 3, are we safe to say that x is never exactly 3? We're safe to say that. So as long as x is not 3, we're okay. X is approaching 3. Let's just strike those. It's some number over itself, some non-zero number over itself. So what we're really evaluating is what's left, which is x plus 3. And what does x plus 3 approach as x approaches 3?
6.
It approaches 6. Now, if that disturbs you a little bit, that we said here that x can't be 3, but it's okay that, 38 seconds later, it's okay that x is 3. We're in a sense not doing that. X is not exactly 3. We don't necessarily ever get exactly 6, but is it true that we're approaching 6? It is true. So I'm not really putting in 3 here. We're putting in a number something like that, right? Or something like this. But it's kind of annoying to write those numbers down. So we just say that it's so darn close to 3 that we're just going to call it 3. So we're going to approach 6. So it is permissible to say that the limit is 6. That's a limiting value. Doesn't mean we ever get there. So we may have to do a little bit of algebra. Let's continue with any questions about that before I move it. So don't ever write down 0 over 0 for an answer. That's just an indicator to you that you've got to do some more work. Let me see if we can handle this problem, and then I'll try to get a situation or a scenario created that would result in this problem. That looks like kind of a strange problem. 2 plus h cubed minus, and it's 2 cubed, or 8, all over h as h approaches 0. Some of you have had some calculus in here. Is this a direction that we ought to be headed, that h is approaching 0. Is that going to steer us toward the derivative? Some of you have had some calculus, right? Does that look like a familiar problem? We need to be able to handle h approaching 0 when it's got this function of numbers and h's and try to algebraically work this thing out. Well, can we use direct substitution?
No.
If you did, what would you get?
0.
0 over 0. So here's another problem where 0 over 0 isn't going to get us anywhere. Any suggestions? There's actually two, I guess, pretty good approaches to what we could do.
Perfect cube.
Okay, we've got the difference of two cubes, right? Do you remember how to factor the difference of two cubes? I don't recommend that method, by the way, but that we will have a problem in a few minutes that's a little simpler than this one, where we do need to factor the difference of two cubes. But that would work. Anybody see an alternate method? So let me write this up here. We're going to come back to this. That may be something that you remember, the difference of two cubes. I know you know the difference of two squares. We just did that. But we need to be prepared to factor the difference of two cubes. Could we just cube this? 2 plus h, right?
Mm-hmm.
When you cube something, first term is what?
2 plus h.
Is the first term of that binomial cubed by itself.
No, that way.
Okay, next term is
3 squared.
3 times 2 squared h to the 1. Is that right? Next term,
3
3 times 2 to the 1 times
8 squared.
h squared, and then h cubed. So in general, I can tell by your expression that you're not really liking that all that much. Isn't this x cubed plus 3x squared y plus 3x y squared plus y cubed, right? Does that look a little better in that form? How do you get the coefficients? The coefficients are 1, 3, 3, 1. Anybody remember how to get the coefficients when you cube a binomial? How'd you get them? Remember, you told me to write down 3. You're just randomly picking a number that...
No, sir, it's Pascal's triangle.
Okay, Pascal's triangle. So the coefficients of some,
1, 4, 6, 4, 1.
right? So this would be a binomial to the 0 power, right? Coefficients would be 1. Something to the 0 is 1. This would be a binomial to the first. A plus b to the first is 1a plus 1b. Here's a plus b squared. A squared plus 2ab plus b squared. Here is some binomial cubed. We have x plus y, x1, x cubed. 3 is the next coefficient, right? 3 is the next one. So the next line would be
4, 6,
1, 4, 6, 4, 1. And we could continue that process. I'll actually give you another kind of an algorithm that's a little different from that as we progress through this chapter. But we need to be prepared to raise some binomial to the third or to the fourth or to the seventh if we had to, and without necessarily depending on Pascal's triangle. So what do we have here? We've got 2 cubed. Let's take this line and write it back up here where we've got the problem going. 2 cubed is 8. What do we have here? 4, 12h. Is that right? Plus 6h squared plus h cubed. From that, we're going to subtract 8. And that's all divided by h. Now, can we still not use direct substitution? We're still kind of strapped here, aren't we? If I plugged in h equals 0, again, we're still in trouble. Let's see if we can avoid the trouble. 8 minus itself, does that help the cause? A little bit. What is true about every term that's left in the numerator? Has an h.
Factor out H.
So it's in 12h 12 times. It's in 6h squared 6h times. And it's in h cubed h squared times. It's getting a little too cluttered here. Let me rewrite this. So here's what we have. Factored an h out in front. We've got 12 plus 6h plus h squared all over h. How does that help? How does factoring h out in front help?
They
Okay,
cancel.
now we see the culprit of what's causing the 0 over 0. We've got an h as a factor of the numerator and an h as a factor of the denominator. There's our 0 over 0. Are we convinced here that h is not exactly 0? Not exactly 0. So as long as it's not exactly 0, that h over itself reduces. So we've got 12 plus 6h plus h squared all over 1. I guess I don't need that. Now what happens? Can we have permission now to let h be so darn close to 0 that for all practical purposes it is 0? So this term goes to 0, that term goes to 0, and we're left with 12. Any of you know when you looked at that original problem, or any of you thinking, oh yeah, 12. 12 is that answer. Okay, I wasn't either. So a lot of times we're stuck with cubing or factoring and reducing, and then all of a sudden it becomes fairly clear what it is we're supposed to do with that. That one okay? Here's another kind of strange one. Let me start a new sheet of paper here. You've done a process similar to this, but I bet you haven't done one exactly like this because you haven't needed it in algebra. Direct substitution? No. We can try it. You can always try it. But in this case, we might get another 0 over 0, right? So it's like we haven't done anything yet. You've used multiplication by conjugates before, but you probably have never multiplied by the conjugate of the numerator. Don't you always, in an algebra problem, multiply by the conjugate of the denominator, right, to get the denominator rationalized, to make it a rational? Let's try this. If you see a radical expression like this, let's try to multiply the numerator and denominator, each piece, by the conjugate of the numerator. Conjugate meaning the same two terms put together with a different SIGN in the middle. That's something non-zero, right, over itself. Can't multiply by 0 over 0, but if t is approaching 0, this would be what? 6, and this would also be 6. So it's legal to do that. What's the advantage gained? What happens in the numerator?
The middle
You
comes
read
out.
square root.
Okay, there is no middle term. I heard that. And what's another advantage? We've got the first term is a square root. So when we square it, there's no more square root, right? So this ought to be the first term squared minus the second term squared, right? A squared minus b squared. Now the denominator is kind of worse for that choice, but I think we'll like what happens. Kind of messed up the denominator. T squared plus 9, the square root of that, the quantity squared, is t squared plus 9. From that, we're going to subtract 9. That helps the cause. Okay, can you see that it helped? What is the advantage gained here by multiplying the numerator and denominator by the conjugate of the numerator? Lose the 9s?
Use the numbers.
Plus 9 minus 9. I like stuff like that. I can handle that. Now what are we left with?
T squared over T squared.
T squared over t squared. Wasn't that the culprit? Right? Because t is approaching 0. T squared would be approaching 0. There's a 0 over 0. There's the culprit. So let's, as long as t is not 0, let me go ahead and rewrite this step. So as long as t is not exactly 0, which it isn't, t squared over itself reduces to 1. So basically the first time we avoid 0 over 0 and we get rid of that, now we're rid of that, then let's try direct substitution, even though technically we're not putting in 0, we're putting in a number that's very close to 0. But for all practical purposes, if t is so close to 0 that it is 0, what do we get? 1 over 6, right? Were you thinking that when I wrote that original problem down? Sure you were. I was too, right? Had no idea till we got to this step of the problem what the solution was. But I knew what I was headed toward. I wanted to get rid of the whatever it was that was causing us to have 0 in the top and 0 in the bottom at the same time. So our limit is 1 over 6. Question on that? So although it kind of complicated things initially, this doesn't look simpler than the original problem. In fact, I think it looks worse. But if we just kind of continue with that, it does get us to a place where we can make things look simpler. Okay, now if you think those are strange, here comes some other really strange ones. Let's graph them first. Let's graph this function and then see what happens. Here's kind of where we're headed. We want to take the limit of this. That's the direction we're headed. So let's get a picture of this. If we do have a problem, right? At 0, clearly there is a problem. So we can't just direct substitute here and expect to get a solution. Anybody want to guess at the answer? How about 1/6? That worked in the last one. How's that sound? Or what was our first answer? 12?
Yeah.
Doesn't matter, right? One of those two. Let's just write one down. 12 or 1/6? How about 12/6? Let's write that down. Kind of a combination of our previous two answers. I have no idea what the answer is here. So let's look at this function. Let's look at a picture of this. Now, if we know x can't be 0, let's say that x is some positive integer. If x is a positive integer, or any positive number for that matter, isn't the numerator exactly the same as the denominator?
Mm-hmm.
Well, when that happens, when the numerator and denominator are the same, what's the quotient? 1. So any positive number that I throw in here, the numerator and denominator are the same. So the y value is 1. Now if I throw in some negative number, doesn't necessarily have to be a negative integer, will the numerator and denominator be the same?
It'll be positive.
Well, the numerator is the
It'll be
same
one, but
number, except it's positive,
Yeah.
right?
negative.
So when I plug in 3, for example, negative 3, it's the absolute value of negative 3 over negative 3. What's that? Negative 1. So a picture of this, if x is positive, not 0, we get 1, right? And if x is negative, not 0, we get negative 1. So there's a picture of this thing. Certainly it has a problem at 0. Now let's go back to the original question, which is the limit of this function as x approaches 0. So that means we've got to be able to come in closer to 0 on this piece of the graph and also on this piece of the graph. Are we converging on the same value from both sides? Clearly we're not converging on the same value. Where are we on one piece? Positive 1. Where are we on the other piece? Negative 1. So what's the answer? No limit. Okay, does not exist. Because we're not approaching the same value from, on this graph, on this picture, from both sides of 0. Does that have an answer? That's a one-sided limit, right? So we're coming in from the right only. What's the answer? 1, okay? Not only is it approaching 1, in fact it is 1, right? It's stuck on 1 the whole way in. So that's just looking at this piece right here. And if we change that then to the other one-sided limit coming in from the left, the answer would be negative 1. So the two one-sided limit questions have an answer, but because they're not the same answer, the two-sided limit question does not have an answer. Does that make sense? All right, that's kind of strange. This one, you'll have to tell me if you've used this before. Come across this in another math class prior to this one. Does that ring a bell for anybody? That notation? No? How about if I called that the greatest integer function? Does that ring a bell? No bells ringing today? So the greatest integer function. So basically whatever x you throw into that little symbolic bracket looking thing, you take the greatest integer that it totally contains. It's not a rounding. In fact, it's a truncating. It's going back to the previous integer. So for example, the greatest integer in 2.1 is 2. The greatest integer in 2.8 is 2. The greatest integer in 2.99 is 2. So if we're not to that next integer yet, you have to go back to the predecessor. So that's a greatest integer function. Kind of a unique graph when we get this thing done. This is a little awkward when you work with negatives. Now think of where we are on the number line. So here's where we are. Negative 1.4. What's the greatest integer that's in negative 1.4? Negative 2. Is that the same thing we just did? We're not quite to -1 yet, so we have to go back to the preceding integer. That looks weird, looks different. But it's the same process. If you're not quite to the integer you're headed toward on the right, then you have to go back to the preceding integer. So what's the greatest integer in -7.1? Okay, we're not quite to -7 yet, so we have to go back to the preceding integer, which is -8.
So it's assuming that you're going towards 0, not away from it.
Well, it doesn't matter. We're not to the integer -7 yet, so we have to go back to the largest integer that's totally contained within -7.1 is -8. We're not to -7 yet, so we always have to go back to the predecessor. So what's it look like? Well, the greatest integer in 0 is itself an integer, right? What's the greatest integer in 1/2?
0.
Somebody said it? 0?
0.
Greatest integer in anything other, all these numbers in here is all 0 until we get to 1. And the greatest integer in 1 is 1, right? 1.1, 1.2, 1.7, 1.8, all the way till we get to 2. And what's the greatest integer in 2 is itself. So it's a step function. 2.1, 2.2, the greatest integer in all these things is 2 until we get to 3, and then the greatest integer in 3 is itself, 3. And then the same thing back here, same exact pattern. It just looks a little strange with the negatives, but you go back to the preceding integer. So there's the greatest integer function. Now let's take any value. Any integer value, it doesn't matter, let's just say 2. Do we have problems at the integer? If we're less than that integer, we have to go back to the preceding integer. If we're right of that integer, then we're at that number, right? So here we are on this picture. We want to get closer and closer to 2, the x value 2, so we're coming in from here and also from here. Are we coming in on the same value from both sides? We are not. So what's the answer? Does not exist, right? So if you pick any integer value, you're in trouble because that's where the two pieces kind of disconnect. But if you pick any other value, .5, well, that's not a problem. As we approach 2.5 from numbers less than 2.5, what's the greatest integer in them? 2. 2.5 from numbers larger than 2.5, what's the greatest integer in them? 2. So in this case, we're okay that the answer is 2, but at integer values, we've got a little bit of a problem with the greatest integer function. Okay, does anything ever really behave like that? I mean, why look at a function like the greatest integer function? Now, I'm not saying exactly like this one, but does anything that we ever graph ever do this, you know, it's linear for a while. In fact, it's even better than that. It's constant for a while, and then when you get to a new value, it jumps up, and then it's constant for a while, and then it jumps up to a new level, and then it's constant for a while. Does anything really behave like that? I think we've done one already this year. Price of a stamp. Did we do that in here? Right? So for a certain amount, you pay the same thing for a stamp, and then when it gets to that whatever mark, that 2-ounce mark, doesn't the price then jump up to a new level? and stay at that level for a while. And then when it gets to the whatever 4-ounce mark, then it jumps up to a new level. So things really do behave like this. Taxi cab fares behave like this. You get in the taxi cab, you're going to pay a flat amount, right? Doesn't matter if you go 2 inches in the taxi or what, the first, what's it normally say, 1/8 of a mile or something like that, something ridiculous like that. So you pay the same amount for that first 1/8 of a mile. And if you're still in the cab when you get to that mark, doesn't the price then jump up to here and then stay there for a while, maybe the next couple miles, and then it does what? Jumps up to there? So those are incremental type problems, and that's exactly what this is. That's I don't think you'll see anything that behaves exactly like this, but similar to this. Okay, the last couple of theorems, let's take a look at them, and then one example of them. Here's what the authors have stated as these theorems, the last two on this page. So if we know that the f of x is basically underneath the g of x, so it's less than or equal to the g of x, near this value a, and again, we don't care what's going on at a itself, and the limits of f and g both exist as x approaches a, then we should expect the limit of the underneath function to be less than or equal to the limit of the higher function. I don't think there's real rocket science in this one, right? The function itself was less than or equal to, therefore we should expect the limit of the function as x approaches a to be less than or equal to. And then we kind of put two of those together on either side, and we come up with this thing called the squeeze theorem. Comes in handy now and then when we're trying to evaluate a limit. If we know that f of x is the lesser function, we go up a little bit, and there's the g of x, and we go up a little bit further, and there's the h of x. And we know that the limit of the f of x is L, and we can also determine that the h of x also has limit L. What does that tell us has to happen with the g of x? What's the only way that inequality could be satisfied? Is if the two outermost extremities are getting closer to L, doesn't that force the one in the middle to also be approaching L? Right? So if this is approaching L, the lesser one, and the larger one is also approaching the same number, L, that forces the one in here to also converge on L, which is what this says. Let's look at this in picture form. So let's say that the f of x is down here. Let's say that the h of x is up here. And let's say that the g of x is somewhere in between. So here we are. We're coming in here to some x value a. So if the f of x is closing in on some value, let's say L, does that look like that's true about the f of x? Not a wonderful diagram here. Does it look like the h of x is also kind of squeezing down on that value L? Well, if the other one is trapped in between these two, and it has to stay between them, and they're both headed toward L, where does it have to go? It has to go toward L also. It's being squeezed by the other two, pretty appropriate name for the theorem, that if this one is headed toward L and this one is headed toward L, then certainly the one that's being sandwiched by those two is also headed toward L. So that's going to the letter L. I better not say going to L. That kind of sounds like something else, doesn't it? The h of x is going to L. Well, those are the kind of the ones on either side of this g of x. Well, then g of x approaches L as well. Let's look at one example of the squeeze theorem. Suppose we want the answer to x is approaching 0. Guesses? Can't do direct substitution, right? We're kind of in trouble. Cosine of 4 over 0. I don't think we're going to be able to look at it and just jot down I mean, I will. Any guesses? 4? Sounds like a good number. 0?
1.
1? Okay, it's kind of a wild guess right now. Tell me about this term right here. I don't care what that is. It's the cosine of something. Isn't the cosine of something, as long as it's not, 4 over exactly 0, which it will never be, isn't the cosine of something always between 1 and negative 1? Right? Everybody convinced of that? So it could be the cosine of some ridiculous 2 pi. It could have all kinds of stuff in it. But if it's the cosine of something, it's somewhere between 1 and negative 1. Now, could I multiply through this inequality by x squared? Is that legal? X is not 0. Even if it were 0, that'd be legal, right? I'm going to multiply by x squared and x squared. So every piece of that inequality gets multiplied by x squared. Now I think we've got the squeeze theorem set up here. That's kind of the lower end of what could be going on this function. This is the upper end of what could be going on. So what is the limit of negative x squared as x goes to 0? And what is the limit of x squared as x goes to 0? What's the answer in both cases?
0.
0. Now back to our original problem. Isn't that in the middle? If its lower end goes to 0 and its upper end also goes to 0, doesn't that force the thing in the middle to go to 0? Right? So therefore, the limit of x squared times the cosine of 4x as x goes to 0 by the squeeze theorem. So it's a whole lot better to work with negative x squared and x squared than it is with that ridiculous mess we started with. So if they both go to 0, the one in the middle must also go to 0. That is squeezed to 0 because of what's on either side of it. Okay, bring your questions over anything. Chapter 2 questions. We'll try to deal with those tomorrow. Let me give you some problems here from this section to look at. Questions about these are also fair game tomorrow. There are some excellent problems in this set right here. Okay, and that'll finish us for today.